Okay, so this is a video for a past year paper, which happened to be last semester. My paper, the one I personally took. Yeah. So this heat transfer, semester 1 of the academic year 23-24. I'm doing this in celebration of 300 subscribers. Yeah. So thank you for your support. Let's get started. So heat is generated in a uniformly with this volumetric heat generation rate in a sphere of this diameter. And then it is being cooled by a fluid with this ambient temperature. And the heat transfer coefficient is not a value. It's not a constant value, but it's a function. It's a function of the surface temperature and the ambient temperature. Okay. But in the end, these two values are also constants, right? So actually this whole thing is a constant. Yeah. It's just that we do not know what the surface temperature is. Okay. The thermal conductivity of the sphere may be assumed to be constant. Okay. So it's important to know that K is constant. So this is your K. What are the temperatures of the surface and the center of the sphere under the steady state conditions? Okay, so we're focusing on steady state conditions. State all the assumptions made. Okay, so I'm going to assume several things. I'm going to assume that radiation is negligible. Radiation is negligible. I'm going to assume that this is a 1D problem. So even though this is sphere, we're not going to see it vary in the angular directions. Okay, so theta and phi. Yeah, I'll get to that when I talk about solving the equations. So 1D problem. So K is constant. Okay, actually H is also constant. Okay, H is constant. Yeah, because Ts and T infinity are constant. So I realize it's not a function. It's actually just a constant also. It is constant and uniform. And uniform over the sphere. Okay. Yeah. If I'm missing any more assumptions, you can comment down below. Okay. Yeah, but I think these are more or less sufficient. Yeah. If I'm missing anything, you can comment down below. Okay. Then let's get started in the actual details of the solution. So what do they want? Our objective is to find the surface temperature. So temperatures of the surface and the center of the sphere. Meaning to say, our objective, find the surface temperature, which is Ts. Okay. And uh, and the temperature at the center of the sphere. Okay, so we denote it like this. Okay, I'll talk about why we denote it like this. Actually, I'll just talk about it now, right? Because we're going to be using because we're thinking of a sphere, right? We're considering a sphere. So sphere, obviously, we have to use the spherical coordinates. So since I consider this to be a 1D problem, I don't see it vary in the theta and the phi direction. Meaning to say that the center is characterized. Okay, so if this is a sphere and a radial position r is given like this, then the center must be where r is equal to 0. That's why I denote it as t where r is equal to 0. Okay, yeah, so our objective is to find the surface temperature and the temperature at the center. So let's draw out the problem, right? Always, I recommend you to draw the problem. In fact, I strongly encourage you to draw the problem so you have an idea of what is going on. So we have a sphere, right? And then the center of the sphere is given as this. The radius, okay, because the diameter is 15 cm, which is 0.15 meters, then this implies that the radius will be half of this, right? So it'll be 0.075 meters. Okay, so the radius occurs at 0.075. So this is the center where it's 0. Yeah. And then it's losing heat. It's losing heat to the surrounding via convection. So T infinity, they say 0 degrees Celsius. And the heat transfer coefficient is given by 2 plus 5.8 times Ts minus T infinity to the power of 1 over 4. Now look at this. Because they told us that t infinity is 0, right? So we can get rid of this. And then ts is the only thing in the bracket. So let me get rid of this and change this to ts to the power of 1/4. Okay, so this is our heat transfer coefficient. And we do not know what this surface temperature is. Okay, and keep in mind that there's heat generated inside this sphere at this rate. And the sphere has a K of 3. Okay. Yeah. So first thing first, let's calculate the surface temperature. And the way to do this is by considering an energy balance. We know that energy is being produced within this within the sphere. Okay, so energy is being produced in the sphere, and then after that it's being convected away into the surrounding fluid. Okay, so energy is produced in here, and then it convects away into the surrounding, okay, to T infinity. So we can take an energy balance. So you consider the sphere as a control volume, okay? Consider a control volume that encapsulates the sphere, and you write down the energy balance equation. E in minus E out plus E gen equals to E stored. Okay? So now we try to simplify this. So ask yourself, is there any energy going in to the sphere? And the answer is no, right? Because we know that energy is being created inside here. Okay, energy is being created inside here, and that it leaves into the surrounding fluid by convection. So you see, there's no arrows pointing in. There's no energy going in, so this is 0. We know there is energy going out. We know there's energy being generated, and because this is a steady state condition, right? This is a steady state problem. This will be 0. Okay. So you rearrange this, you get E gen is equal to E out. Okay, so E gen is equal to E out. Now let us substitute what we know to satisfy E gen is equal to E out. So we know that E gen is equals to E out. Now what is big letter E gen given by? This E gen is given by small E gen multiplied by volume. Why? Because big E gen is in the units of watts, whereas small E gen is in the units of watts per cubic meter. So since it's in a per unit volume basis, we have to multiply by the volume to get the actual energy generation. So E out is given by convection, right? Because heat is lost to the surrounding fluid via convection. Okay, heat is lost to the surrounding fluid via convection. So we replace E out using the Newton's law of cooling, which is the convection formula. So H A Ts minus T infinity, right? Ts minus T infinity because it starts from the surface and then it goes to the surrounding fluid. Okay, so you're using the convention T start minus Tn. Okay, then yeah, let's continue to substitute. So E gen is given by 10,000. Then we're dealing with a sphere, right? The sphere, the volume of a sphere is given by 4 over 3 pi r cubed. So 4 over 3 pi r cubed equals to, now, H bar is given by this formula, right? It's given by this formula here, so you just plug it in. So 2 plus 5.8 times Ts to the power of 1/4 multiplied by 4 pi. Yeah, so area of a sphere, the surface area of a sphere is given by 4 pi r squared. And then T infinity is 0 degrees Celsius, so we can throw that away. The only term we're left is Ts, so you multiply by Ts. Now, this is a polynomial in terms of Ts, right? There's one equation and one unknown, but the thing is, it's not easy to solve because of this Ts to the power of 1/4. So the only way I can see about going through this is using our graphing calculator. So using the graphing calculator. So graphing calculator. So let's have a look. Okay, so you open up your graphing calculator, and what you're going to do is you plot each side of the equation. So on one side we have the E gen, right? So we have the 10,000 multiplied by 4 over 3 pi r cube. Yeah. Okay, 4/3 pi r cube. Then after that, you plot the right-hand side of the equation, which is the E out term, the convection terms. So you have 2 plus 5.8. Okay, TS is our unknown. That's why I'll label it as X. So 2 plus 5.8 X to the 1/4. Then multiply by the surface area. So 4 pi r square. Then you multiply by the surface temperature X. Okay, so now we have to find the intersection between these two lines. So let's go ahead and fit the two curves, so fit them. Okay, we still cannot see the other curve, so you zoom out. So try to zoom out. Okay, so we see the two curves. So what we're going to do is find the intersection between the two curves. So find the intersection here. Okay, so they intersect at hold on. Here. Okay, so they intersect at this value where TS is equal to 17.93. So let me capture this. And let me switch back to my OneNote. Okay. So we know it intersects at where T is equal to 17.938. Yeah, so this is our surface temperature. So we've already found the surface temperature. Now we need to find the center temperature. Now, the temperature at the center, see, the temperature at the center is when we had the function T of R, but we substitute R is equal to 0. But the thing is, we do not know what this function is. So we have to find that function ourselves. Okay. And this is basically the I think the first two tutorials are done. Okay, so the first two tutorials are done, I outlined this method. So what you do is you need to get the spherical coordinate equation. Okay, so I actually didn't obtain it yet. So let me pull it out. Yeah, so you open your lecture notes to find it out. So let me grab it from my notes. Okay, hold up. I have it. Okay. Yeah, so you go to your lecture notes and obtain this equation, the spherical coordinates equation. Why the spherical? Because we have three choices, the Cartesian, the cylindrical, and the spherical. Obviously, you choose the spherical one, right? Because we're dealing with a sphere. So remember my assumption? My assumption that this is a 1D problem. 1D meaning to say that temperature is not a function of theta, it's not a function of phi. Okay, so let me say that again. Temperature for 1D problem, if I say that it is a 1D problem, that means temperature is independent of theta and phi. So temperature is not a function of theta. It is not a function of phi. Okay. And because it's a steady state problem, it is not a function of t as well. Okay. So if I say that they are independent of theta, for example, so that means d theta will be equal to 0. If I say that it's independent of phi, that means d theta d phi is equal to 0. Okay, so that means wherever you see the d theta d phi, you change it to 0. See, you see it over here and over here. Okay, so the whole theta and the whole phi terms, you can just remove it. Okay, so this becomes 0, this becomes 0, and the reason being is because this is a 1D problem now. Okay, and this one is also 0 because it's a steady state problem. Okay,